Welcome back to ECE 320A. We're still in Unit 6, and this particular video we will be formally defining poles and zeros and illustrate those concepts with an example. Poles and zeros arise from linear time invariant systems or the transfer functions of linear time invariant systems. Here is one such transform. It could actually, I guess, poles and zeros arise from the Laplace transform of a signal, but typically we're talking about poles and zeros associated with a system, but it could be the combination of a signal and system, etc. But here is the same transfer function written in polynomial form in blue, and we see that it's strictly proper. It's also monic. That's another term that we may introduce. Monic means that the leading coefficient in the denominator has been normalized to have a coefficient of 1. If there's some other coefficient outside or weighting the highest power, we would simply factor that out from the denominator, and we could then absorb that coefficient in the divisor of each of the numerator coefficients in the previous numerator. Here we've already normalized the leading coefficient, so this is a monic polynomial, and that just means that the leading coefficient in the denominator has a coefficient of 1. The second form that we have described or written the transform in is factored form, and here we've explicitly factored the denominator into linear factors and quadratic factors. The quadratic factor here, the way that it's written, hopefully you see that this particular quadratic has roots that are equal to -3 plus and minus j3. So if that doesn't appear obvious, go ahead and substitute s equal to that, one of those two, and you'll find that both of those values for s do cause that particular quadratic polynomial to vanish or to become equal to 0. You can now see that we have two linear factors in the numerator, we have a linear factor in the denominator, and we have a quadratic factor in the denominator that leads to complex poles. We want to now identify for these transform expressions, and sometimes we'll label the numerator maybe as a polynomial capital N of s, and the denominator labeling that or defining that to be a polynomial capital D of s. We now want to define formally these concepts of poles and zeros. First, we are looking for particular values of 0 or values of, gave the answer away, values of s that cause capital X of s, the entire transform, to equal 0 are in fact called zeros. And if you look at this, since it's strictly proper, the numerator degree is 1 less than the denominator degree in this particular case. Strictly proper just means that the numerator degree has to be less than the degree of the denominator. It doesn't have to be just a factor of 1 different. But let's now make the distinction between zeros or another type of 0, which is that associated with the values of s that cause the numerator to equal 0. And you may have thought, well, that's the only way that capital X of s can be 0, is if we find s's that cause the numerator to vanish. We will actually call those zeros distinct from the previous definition, but we will call, and typically we'll just say zeros, but let's now say that values of s that cause the numerator to equal 0 or to vanish are called finite zeros. The reason I say finite zeros is because the denominator is larger ordered than the numerator, we could actually have an s going off to infinity that would cause capital X of s to vanish. And that would be an infinite zero. So we could have an infinite zero in this particular system because of the strictly proper nature of it, and we have two finite zeros. In this particular case, if we look at this system that we have, our zeros are now located where the finite zeros, that, like I said, I will probably many times just refer to those as zeros, the values of s that cause n of s to vanish, it should be clear that s equals, so set each of those factors to 0, and that then says that s equal to -1 is a finite zero, and s equal to -3 is a finite zero. We represent those, if somebody were to sketch those in a complex plane, we would represent zeros as open circles on our complex plane. And here we locate an open circle at s equal to -1 and another open circle at s equal to -3. Those are now finite zeros associated with this transform capital X of s. We can contrast that with the notion of poles. Values of s that cause capital X of s to become infinite are called poles. And values of s that cause the denominator, capital X of s, the denominator of capital X of s equaling capital D of s to equal 0 are called finite poles. But typically, if I leave off the adjective, I'm usually referring to finite poles and finite zeros, and I may just denote those as poles and zeros. If we find values of s that cause capital X of s to go to infinity, those are the values of s that cause the denominator to equal 0. You should be able to see that we now have 3 of those since we have a third order denominator. One of those poles is at s equal to -5. That causes that linear factor to go to 0, or capital X of s to go to infinity. And either of -2 plus j3 or -2 minus j3 cause that quadratic factor to vanish, causing the entire transform capital X to go unbounded. So in this case, our poles from our example, we have 3 of those. We had a third order denominator. One was at -3, and 2 were complex conjugates, -2 plus and minus j3. In contrast to how we indicate zeros in the complex S-plane, we indicate poles with x's. So if you wanted to think of these as arrows, infinitely long arrows, the tail of the arrow would be the pole, and we had a pole at -5 and another pole at -2 plus j3 and another pole at -2 minus j3. Now you have infinitely tall poles at those x's, and you could think of thumbtacks at the zeros, and now imagine a circus tent that's made out of some rubberized sheet fitting on top of those poles and being forced to the ground or forced to 0 with thumbtacks at those 0 locations. And you can start to see or imagine this tent hovering above this complex S-plane. And if one were to walk along the imaginary axis when S is equal to j omega, then that particular location where the circus tent, what is the height of the circus tent, this rubberized sheet above that frequency axis, the j omega axis, would provide you with a magnitude of that system's frequency response. And that tells you then how the system is going to behave at particular frequencies. If you wanted to know how is the system going to behave at a value of, or at a frequency of 1 radian per second, you would look up and see what is the altitude or height of the circus tent above that point, and that would now tell you how the system amplifies or attenuates a signal at a frequency of omega equal to 1 in response to being passed through a system that is governed by these 2 finite zeros and these 3 finite poles. I could also provide you with a pole zero pattern on an exam, maybe like this, and ask you to tell me what's the structure of the time domain response associated with this pole zero diagram. So if I give you a pole zero diagram, you should be able to tell me what the transfer function poles and zeros are. If I give you a transform expression, you should be able to factor the numerators and the numerator and denominator to provide the pole and zero locations associated with that system. But once you have the pole zeros, you should be able to then, either given capital V of S or indirectly by the pole zero diagram, you should be able to tell me what is the structure of the time domain signal associated with the pole zero diagram or capital V of S. Looking back at this pole zero diagram, what influences the structure are not the zeros, but the modes are influenced by the pole locations. The zeros shape the transient response, but they do not determine the modes of the response. We have one mode that's purely exponential. It's e to the minus 5t. We have 2 other modes that are oscillatory because they have an imaginary component. That imaginary component is 3, and that's then the damped frequency of oscillation, and it's also, those poles are located into the complex S-plane in the left half plane, giving them a negative part, so they also have some exponential damping to the amount of e to the minus 2t. So if you now see those poles, you can now write down very quickly that the structure of V of t is some coefficient a1 weighting the mode at due to the pole at minus 5, which gives you this exponential e to the minus 5t, and then you have sines and cosines that are exponentially damped, and let's say that they are weighted with a k1 e to the minus 2t. That's their exponential damping. The cosine has a frequency of 3. That's due to the imaginary component of the pole, plus k sub 2 e to the minus 2t sine of 3t, t greater than or equal to 0. That would be one acceptable form for the structure of V of t. Another one, knowing now what you do know about combining sines and cosines of the same frequency, whether those are damped or not, you could also say the structure of V of t is a1 e to the minus 5t plus, let's say, b e to the minus 2t cosine of 3t. We can't change the frequency when we combine 2 sinusoids at the same frequency, plus some offset or shift in time, t greater than or equal to 0. So in this particular case, you can see that you have 2 unknowns, k1 and k2. In this case, you have a magnitude and an angle, or again, 2 unknowns that are different from the modes. We have modes at e to the minus 5t, and we have modes due to the exponentially damped sine and cosine. And that's now what you should be able to conclude by looking at this pole zero pattern, or given a capital V of S, you should be able to factor its numerator and denominator. And once you know the poles or the roots of the denominator, now you know immediately what the structure of that time domain waveform would be.